So our next speaker is Egor Bogatov from Microsoft. You have the final presentation on our conference, and what do you think? Will you break their bearings? Well, yeah, it's a tough topic. It's a topic that is unclear whether you need to spend many hours on some basics of design compilers, or just to talk some interesting things that are interesting mostly for compiler engineers. That's not too many of them, and so I did my best to really make an interesting presentation to motivate someone to just, take the source code and understand it, because it's not as difficult. How did it happen that you started working on JIT CLR? Well, yeah, it's not my primary job, as I have working in mono runtime, and I also, I work with JIT, LLVM-backend was my interest for a while, and you could, mark the LLVM code, and the only issue was how to emit it properly, and then I started to dig into LLVM and compare CodeGen with JIT, CoreCLR, and found a lot of missed opportunities there, and decided that I would like to do those micro optimizations in JIT. And the code in JIT is quite pleasant. It's beautiful. The architecture is nice. It's easy to understand. It's quite easy to implement to debug it, and to implement some new optimizations. So if I get it right, you've mentioned that it's not your primary job. So how the JIT code base thinks of contributors? You are from Microsoft. You are not a foreigner. What happens if some foreigner comes? Well, for them it's absolutely the same. I am the foreigner as well as any other would be. It's like 6 people there, and I am super foreigner for them and stranger, and I was helped by everyone without any discounts, because I'm Microsoft or whatever, so they helped me in the comments. I took the optimization that existed there, took another one. My first optimization was a micro optimization. It's in the compiler, of course, it's the easiest thing, like microcalls. And my first optimization was like when we divide float by 2, you can replace the division by multiplication by 0.5, and multiplication is 5 times faster than division. Everyone writes, divide by 2 instead of multiplying by 0.5, and you can find that pull request, and this was the beginning of my open source career in JIT. And this has like roughly 40 comments, people helping me to finalize it. Yeah, I saw this GitHub issue, the pull request that where you were working on that optimization. Great. So if some of our viewers and visitors of the conference decide to run that pull request, will they be helped the same way as you were? Is there a chance for them to be helped? Yeah, absolutely. I do a lot of help myself, because I understand that I started from pip calls, but I try to put my hands everywhere on all the phases, and I think that I can be helpful to newbies and JIT team, and also they have a lot of workload. They can, there can be delays in their replies, but usually they do help. Well, great. Yeah, I wanted to say that JIT can be in a way easier to contribute than some specific base classes on C#. Well, sounds interesting. On that optimistic note, let's switch to your presentation about the JIT compiler. You have the word. Thank you. As you've mentioned, I am Egor. I work for Microsoft. I do different things. But half of my time I spend on JIT changes in CoreCLR and Mono, and it's really interesting for me. Unfortunately, it's very high level because 40 minutes on JIT compilers, it's like 8 hours, should be 8 hours. So here is our agenda. And let's look at how it works. Let's focus on inlining a bit because it's the profitable optimization. Some techniques that I used in all the compilers, the safe form and value numbering, used in all the compilers nowadays, and a couple of control flow optimizations and code gen. So let's start with this simple slide. I won't spend too much time on generic slides. This is a schema of what is going on with your C# code after writing C# code and before it's run in the CPU. So it's converted using Roslyn into IL code. It's the same between different languages. C# is also compiled into IL. And we get the IL, intermediate language, managed one. Then we put it into the core host of our runtime, small executable of our runtime, and passes the control to the runtime, and then the runtime orchestrates, initializes all the subsystems, domains, up context, set, JIT, and first thing it does, it says, well, I've launched and I need to compile all those methods, and then it calls JIT and calls GC. So it's a library on C or C++, same as all those three, and JIT compiles it into machine code, and then it runs on your processor. So the theoretically minimal self-contained app looks like this. So we have core run launcher, we have a GC, we have JIT, we have a small runtime, our application Hello World app DLL doesn't do anything, 4 kilobytes, and our system private core lib, MS core lib, the base library containing pretty much everything. Many things are in different libraries like system console, system link, cryptography, but all the base types, base things like environment and stuff like that, are in this library. That is why it's so big, 1.8 megabyte. It's after the stripping. So if you'd like to implement your own JIT, the interface for talking between runtime and JIT, it's this small. It's like 2 methods, roughly 1 method, compiler method. As soon as you've implemented this interface, you are now in JIT. Everything that you need is like those 3 parameters, and the main one is info. That has the IL code that you need to compile. The third one is some flags, not interesting, and the other 2 are return values, the beginning of the code and offset, the length. And the first one is an interesting one, is a link. When the runtime asks you to compile the code, it throws you the link to itself, because JIT will need the support from runtime. You don't need to implement this interface, but it's like hundreds of methods that will be helpful for your JIT. So here's how it looks. Here's the JIT's interface from runtime. If you'd like to create your own runtime, then you need to implement this interface. To implement, your runtime for the existing JIT. So here's the interface. It has the methods of like, hey VM, tell me about this field, the type of this field. As the JIT runs, as during the application run, it should know whether the type is already statically needed and converts static read-only fields into constants. Also, there's a method that turns literals into string objects. Works in GC. That's how JIT addresses the GC, because it just asks to implement LDSTR token. Then JIT inline code also asks the runtime, if you don't mind if I inline this, and JIT emits a call to your runtime. Like when we would like to unbox something or box something, then we emit this call into runtime. That will do the boxing, working with GC and copying from stack to heap. So this interface is much harder to implement. JIT works in a lot of phases, and each and every phase works roughly like this. High-level overview would look like this: 8 big phases. First thing, we just import the IL code, open the DLL that is issued by the runtime, and import it into an IL. All the modern compilers use the IL. C++, Go, Haskell, they all use ILs. And the tree-like language in our JIT compiler is an IR. So first thing we do, we import the build into IR, and then we do the inlining. First phase, inlining and morph. Just change the trees a little bit, local optimizations, then we do the control flow optimizations, the blocks, the ifs, the cycles, then it's converted into SSA and removal of the dead code. I will talk more about this, it's just an overview. Then we do the range checks. I talked a lot about it in my previous presentations. Then the lowering, micro optimizations that are close to code gen, then register allocation and code gen, and then emit of what we've generated to run it on the processor. So let's talk about those phases in more detail. So to show you this intermediate language, tree-like structures, let me start with this simple example of 2 arguments where we do something with them and return them. So here's how the import looks. Roslyn will compile this method into this language. Some of you probably saw it, people that work with emit, like aspect-oriented programmers would touch the IL code. It looks like this. Throw arguments, we throw the constants, multiply it, edit, and return. So all those hipster syntaxes are parsed by Roslyn. JIT also parses it, but it's much easier for JIT because there's no pattern matching needed and the context is not needed. And here is how it is exported into the IL. We have only one basic block. If you have a number of cycles, you will have a number of basic blocks. We have only one statement. The first node is return, then it's add. So it's y plus y and y plus 2 multiplied by x. The left node is multiplication, where we multiply a constant by the local variable, and then the second argument is here. So here's how this tree-like structure looks. So the micro-optimization in global morph one of the micro-optimizations in global morph will turn 2 multiplied by x turn into x multiplied by 2. That will simplify the work for the further micro-optimizations. Or also, there's an optimization that turns 2 multiplied by x turns into left shift. It's of course optimized in Lea on x86, but okay. So here's how global morph works. I will talk about it more. Maybe it seems complicated, but I hope it will get easier to understand further on. So those drawings that I showed is how JIT dumps these 3 information. So for all the methods, you will be able to get that picture using that com plus JIT dump. It will not work on the release.NET version. You will need a separate JIT build for that. So you can have a compilation for the whole method before the application of the phase and after. So things like I showed on the previous one, 2 multiplied by x, and after that morph you have left shift and the constants that are switched. The order of the constants is switched. So this tree-like language, all the nodes that I showed you, all the leaves, okay, all the nodes, they have roughly this structure. It's a structure with the first operator that describes whether it's multiplication or division or whatever, or call. So it's a num. Then it's types, integer, non-integer, some fields. There's value numbering pair. We'll talk more about it. So here's how it looks. So all the nodes are different only by that GT opera, the type of the operator. But as with different operators, we need some separate fields. We have some inheritance things. Like with operations, we have gen3 op, which adds the field that is a link to another child, because we need another child here in this tree. Or to the right, you have a constant, a string constant, that would give you 2 fields that describe the string literal, and from a binary operation we inherit another operation where you can store 2 nodes. So here is how the hierarchy looks. It's not all of the subclasses of this Gen3, and the ones we are interested in, it's Gen3 op. It can be multiplication, division, addition. So you have your own operation, Gen3 local var. You have them for intrinsic, for cast, for indirect access, for box. And based on this AR example, if you would like to create a node, a multiplication node in pseudocode, it will look like this. With Gen3 op, you define operator 1 as a local variable and Gen2 as a constant 2. It's the same. You can use the same approach to modify any node, because you can access any node. So the next phase after morphing and import is inlining. Many would not know about it. I have a whole blog about this. But inlining is like to take part of the method and inline it into a call if it's small, like less than 200, less than 20 bytes of IL code, 43 bytes of IL code. It's throwing exceptions. Will it be inline? They say no, it's with exception, it's big, but in reality it will be inlined. So this constructor is a method, and it's called in this test below. Let's see why. So the first thing JIT does is an estimate of a native size. It will go through all the IL code and all the operators and run an estimate of the final size. So we see quite a significant final size. Maybe it's the amount of bits. So new option throw
The IL code keywords have very high weight. So throwing an exception is a lot of assembler code. And we see the final size is quite high, quite big. So to inline this all, we need to have very good reasons. So the formula for that can be inlined is call side, native size, multiplied by benefit multiplier, some thoughts that make the JIT things that it makes sense and should be bigger than call native size estimate. So how can you get that benefit multiplier? It's some observations by JIT in the call side that will enable it to inline big methods. So the first observation is that the method is called inside of a cycle, meaning that it needs to be tried harder to inline it. So the benefit multiplier is, we add a 3 to benefit multiplier. The next, we see it's a promotable structure. It will be sent through registries, not through the stack. So it makes more sense to inline it. It's a constructor, an additional observation saying, yeah, it needs to be inlined. And the most important thing is that here below we pass the constant HRB, and JIT sees that we've passed the constant and it's compared with another constant. So when we inline this, it's a comparison between one constant and another, and you can fold it and delete the whole branch, meaning that the code will be much smaller than what we have now. So it definitely makes a lot of sense to inline it. The result benefit multiplier is 11.5. So, and if we dump our, use the same environment variable to run the dump compilation of a method, then we will see a log where everything I said is there. So we have observations, native size estimate, and so on and so forth. And in the end, we see JIT making a decision to inline it, because the threshold is less than the number there. So it makes sense to inline. The next phase is makes sense after the previous one, and CFG optimization, when we have B equals C. But after the inlining, this code often appears. So here's how it looks in basic blocks. So this code actually has 4 basic blocks. We come from somewhere into this method, we have a basic block for the conditions, and it has 2 arrows, either an exception call or the code that is after that condition. So after B1 we don't have an arrow because it all stops. And as I said, there's an optimization that will just fold it into nothing. So B equals C is nothing. We won't go the way of throwing new exception. We just go to basic block 2. So layout optimization just deletes the blocks that are unreachable, the blocks that we will never visit. It's like basic block 1. So here is the code we have, and then we see that in basic block 0 it just goes to basic block 2, and we just get this code and throw away the whole expression. And in the SSA form, which is used in pretty much every modern compiler, I don't know why I moved it here, okay, but anyways. So it sounds simple, but this is the form that is used so that all the variables are assigned only once. They will all be immutable. So any code can be turned into this, and it simplifies all the other optimizations like allocations, removal of the dead code, copy propagation. So it simplifies the code a lot in Go, in
LLVM, C++, and so forth. So we have this code where we call the method and pass it to x, and is assigned twice. And after the rewrite of the forms, we have x1, then x2, then y is defined. And we don't have any variables that are assigned twice. And immediately we can see that x1 is not used. So y is assigned x2. So x2 is eliminated immediately, and we remove that store very fast. So with this copy propagation, we see that third column with y being assigned x2, and we can just put y into that x2. So the code propagation, the only difficulty is that when we need to change the variable, the x is already assigned some meaning, but we assign some different meaning, different value to it with one condition. And this is solved with those key functions that work like this. So it comes to us in basic block 2, and we say that if you came from basic block 1, then take x as the value. And if you came from basic block 1, then take it from that. So here's how phi function works. And if we look at the dump of this method, we will see that phi node, and it says if you came from there, then take this variable. And in reality, I've even added you the LLVM IR part, that intermediate language. When you use the compiler, it's practically the same. You see phi there that says if you came from that block, take that variable, and from another block, take another. So all those languages are roughly the same, and this is the essence of the LLVM, so to just have one backend for all of them. Value numbering is an optimization that allows you to fold the tough and complex expressions. Here's the code I have. Y is x plus 2, and the idea of the value numbering is that we give unique numbers to all the nodes that I showed you. And with the x, you can assign it the value 1, the unique value 1, and then it will be 2. All the x's will be assigned 1. To all the 10s we will assign 3, and then 4. They are not equal. And x will be assigned 5 because the argument is already has value numbering. We can put the same value there, both to y and x plus 2. We have two exponent calls that are the same number in value numbering. And the whole expression is then assigned the same value, because for JIT we know that all those functions are invariable. So if the argument they got is the same, then the value we return will be the same. So VM is roughly the same here. Then the next tree of this exponent multiplied by constant is different, because we multiply by different constant. And as 10 we have 7, in 11, with 11 we have 8, and the whole expression has 9 as a number. So now we have similar expressions. We calculate them twice, and we don't need to do it, because we can save it into a temporary variable. So if we dump the AR, then we see everything that I said one-to-one with the same idea. So with two intrinsics, the exponent calls, with the same value number, the same VN, 81. because it has its own generation. And if we look at the resulting assembler code, then we will see that the exponential is calculated only once in this code. So we take the registries for floats, we do the plus, and we calculate the exponent, and multiply it by 10, then add it and return the result. So no recalculation of the exponential. So cycle optimizations, there's a lot of them, take a lot of time to run them all. It's quite an important optimization that takes the invariant code from the cycles and it makes it x multiplied by 2. X will not change, so it makes no sense to calculate all the iterations. And what it does, it just removes the invariant expressions outside of the cycle. So it makes a lot of sense. Not that simple, but it's very useful. The Boolean optimization is also, we have a separate phase. It's not very profitable, but yeah, it's interesting to talk about it, like with A equals 0 and B equals 0. Those are two basic blocks, or three basic blocks here, meaning A equals 0 is a separate expression, B equals 0 is another separate expression, so we can fold it into one. So this optimization turns A and into a simple OR. And we can look at this tree-like structure, seeing that we had two conditions that we've optimized into one that just runs the OR instead of ME and not equals. And if you look at the final assembler code, there's no assembler jumps, it's one OR, and we do jump for return or just into the right line. And with the check elimination, range check elimination, there's a simple optimization that whether you have constants or not, JIT will emit for you this check that I marked with red. So it's a long one, and it would make sense for the JIT to check it that if you use the 0 and the 1, then these checks will not be needed. You can avoid running them. Code gen phase looks like this. It's a global switch where we go through all the operators that we have. KT node. NEC is no operations. No operation. So for the node that I don't remember, for integer transformation, then we go to the nodes that are division, or logical and commutative operations, and for all the operations we run the emit for the code gen. So all the magic happened before. All the registers were assigned. I've missed this topic because it will not. I would not have time to do this. And on the code gen stage, we can run some optimizations, like simple ones with code A less or equals 0. So instead of this, we can replace this code with a shift, and this number after the 31 shift, the first bit will be either 1 or 0, meaning that this was a negative number. So this is how this optimization looks. We, in the tree-like structure, op1 is the first argument, op2 is the second one, and if we see that op2 is a 0 constant, then, and the comparison is LT less than, GTLT is less than. So then we emit the instruction of shift right with 31, with the value of 31. So it's a super easy optimization. I spent some time looking for it. We have other examples of optimizations where I had to add some new instructions that were not there. And actually, we found out that it's often very simple. It's like we add one line, and like for I needed a row X instruction for minimal optimization. So just adding it was very simple. So this pull request is changes like very small amount of bytes. And I also started from a very simple optimization 2 years ago, and by that time I've tried different phases of micro optimizations. So what you see on this slide is first page on GitHub. There's a lot of micro optimizations in different phases, and if you would like to try yourself on this, you just open it and try to broaden it, because there's always a field for extra work. I might have forgot some other ideas and optimizations, and use it to create your own. So it's much easier than it sounds, because I don't have any profile education, any education in compilers, any special knowledge, and had no background entering this area. So anyone can do it if you try. So debugging in Windows, Linux, and Mac OS with JIT is quite simple, and as soon as you build the whole project, the solution is built natively, and you open it in Visual Studio, and you are ready to debug it, to run breakpoints and see how the control flow goes in JIT. And for a specific method, you can follow everything that happens and actually put your micro optimization into each and every phase. Like on this screenshot, we have examples with a constant strings, constant lines. I made them invariant, so in variables, so that you could add only one variable there. And what else? The optimized box optimization in instant box and generics. If you look at the assembler code, you will see a lot of boxing happening with generics being mixed with value types. There's a lot of boxing that is not needed, and we can optimize for it. I have an example of an optimization with range checks and null checks in difficult situations. An interesting example is also when you calculate the length of the constant line after the inlining, because when you understand it's a constant, you calculate the line, and then you can make this length a constant, an int constant. Also, there's pull requests that in this says JIT needs to consult with the virtual machine, so I had to throw a method into a virtual machine. So this pull request actually extends the interface for the JIT communication with the virtual machine. So some methods from assignable or value type can be converted into constants, and you can open them and have a look at how they work. So those pull requests are only work on the input phase, and my recommendation would be to read Performance Improvement.NET 5 blog that launched in June. I think it's quite prominent, it covers different areas. And I think it covers JIT and it covers my optimizations. So yeah, it's an interesting one, and it gives you a lot of background on how the approach to performance has changed, how the performance should improve, how significantly should performance be improved compared to .NET Core. With that, I think I've managed to be on time, and I have some time for the questions. Thank you, Egor. It was an interesting presentation. I really appreciate it. And while we wait for the questions from our readers or calls, our free number, I will ask a question that I had during your presentation. So, do I get it right that the depth of the tree that you go through on that phase, forgot the name of the phase, depends on the author of the optimization? No, didn't get it. Can you specify? So you had a part on the about the benefit multiplier when you look through the tree for some depth, and we looked at the constructor, and could this optimization go further in the tree to see that it's called from another structure and so on? Well, actually, inlining is the most important and maybe the most useful optimization, and .NET Inliner is quite limited in what it can do. So one of the JIT authors is actually planning to either use machine learning or stuff like that. It's solved by heuristics, but it's never solved leading to 100% effective code. And with JIT, these heuristics should be very fast, so it's not ahead of time, it's runtime, it's JIT. And we don't have too much time to analyze everything, to go through all the call sites and analyze it in detail, because we don't have that much time for inlining. So yeah, it's heavily limited, but I think it's very important and implemented quite well. As part of the Mona team, I would say that Mona Inliner is very conservative and very simple, and it just looks at the code size. So the only heuristic it has is just code size. Okay, so who decides how much time you have for inlining? Is it a limitation of the architecture of JIT, or the author of the optimization would need to decide? Well, I don't recommend to ask JIT to inline something, except for the case when you know it will fold. But JIT does some tricks to avoid spending time where you would not have an inline. So after the method is more than threshold, it will not be even analyzed. It's just too big. It just makes no sense to inline it. So all those techniques with exceptions and limitation, like there's no use to inline the code inside of the called methods into catch and finally. They are not executed too often, so there's no use in optimizing them. So there's a number of tricks that reduces the time you spend on that. Konrad, in his presentation, said that his dynamic methods are not inlined. And on GitHub issue, I saw... Well, the question is, do you think there's chances it will get into JIT? Answer: yes, I linked the prototype that is inlined, that turns on the inline. So Jan Kotas, the .NET architect, said that it can be done things that I have done is doable, but there will be issues. Like I will run it on a huge amount of tests, and somewhere it will break. So there are optimizations that are easy to run, but not easy to see all the issues and consequences. That's something that happened to me many times. Yeah. Yeah, we know that in the base library in BCL we have special hacks to make the code, to improve the performance of the code, and those optimizations are then go into JIT, and those hacks are no longer needed. Does anyone monitor the removal of those hacks from BCL? Well, it's a good question. I know Stefan Top is doing this, but sometimes we miss that. Yeah, true. We have quite a lot of hacks that need to be deleted because they are irrelevant any longer. But it's a great idea for pull requests for a person who is a newbie and would like to contribute something in the runtime. But it's worth mentioning that we have a layered JIT, and it has a number of layers. So the first layer does not do any optimizations. And if the code is already optimized by the programmer, then the JIT that does not do optimizations will be a bit faster. So sometimes it makes sense to manually optimize it if it's critically important. So the question from our chat, I will try to paraphrase. Method implementation, aggressive inlining can it be ignored by JIT? Yeah, JIT can ignore it, because there are situations where you cannot inline something. There's no way. We don't know how to do it. When we inline the generic method inside another generic method where the generic itself is a known context, like canon type. There are situations where we cannot do it because we don't know how to do it. It's impossible. It has state a lock, and the recent issue we had is, yeah, you cannot inline it. And we had an issue with a lot of code being inlined, like the user put a lot of attributes everywhere, thinking the more you inline, the faster the code works. And when it's inlined into one big method, there's so many temporary variables that JIT cannot track them any longer. It's too many of them, and it decides to emit a very it starts to throw spills into stack, and the code starts working much slower than you just remove this. So aggressive inlining can not only regress the size, it can lead to slow code. So we have a number of examples like this. Then the question is, if the main recommendation is not to use aggressive inlining, then why do we give that attribute to the users? Well, the JIT analyzes the IL code, so it does not optimize the IL. For example, when we check for something equals type of bool with a method that has a lot of switch in it, and we know that in the inlining it will be removed. So JIT can sometimes not see it, and then if I perfectly know that it will fault, I just say inline it. And the second one is when, for example, you benchmark somehow. So if you do it blindly, that will harm your code. And if your idea to contribute this attribute to BCL would be, yeah, you would need to prove